The use of ultra-high strength steels in components and equipment means better efficiency. So you make the machines and components lighter. So lifting weights, for instance, will be lower, and it's more easy to lift. You need cranes with a lower capacity to lift lighter components, for instance. And generally you have a better use of the material. To make the same component half the weight means you need half the amount of raw materials, approximately half the energy to make that steel. So it's a win-win situation. There's one potential problem with ultra-high strength steels. The stronger the steel is, the more sensitive it gets to hydrogen. When hydrogen is a very diffusible atom, when monoatomic hydrogen is entering steel, it can negatively influence the properties and the performance of the steel. There are special terms describing this, for instance, hydrogen embrittlement or hydrogen-induced delayed cracking that can occur. Hydrogen embrittlement is a phenomenon where hydrogen that has entered the steel reduces the steel's toughness. That negatively affects the capability of a steel to absorb impact energy, and therefore we have unexpectedly early failure with unexpectedly low impact energy. This can happen in the car industry for crash parts, for instance, but this happens of course also in machine parts. A good example is bolts, fasteners that are traditionally already on a very high strength level and constantly pre-stressed under high axial tension. Screws, for instance, contain even notches, that means stress concentrators. And when hydrogen is entering such components, by action of corrosion, for instance, then it can lead to this early and unexpected failure. Hydrogen as a single atom is very mobile in the steel lattice. So that means hydrogen, once it gets into the steel at the surface, diffuses then in the solid steel to certain places where it can accumulate. This aggregation of hydrogen is not really big. We are talking here about ppms of hydrogen, parts per million of hydrogen, but it can cause, by localized accumulation, significant damage. It alters certain material properties, certain fundamental material characteristics, and leads to localized embrittlement or localized increased plasticity. And these features trigger secondary problems that lead to macroscopic damage. This happens usually with a time delay, because hydrogen needs to go there, needs to aggregate, needs to create some micro damage that as such is not yet critical, but by further accumulation becomes critical, and that's what we call delayed cracking. That means the failure happens after some delay time and is therefore very unpredictable. This situation is disruptive to production. It is of course extremely costly, because in cases you have to throw away fully finished or mostly finished equipment that you cannot repair. And of course, when such a situation makes it into service, it's a severe risk in terms of the operational safety. So therefore, this phenomenon of hydrogen-induced delayed cracking has shown massive interest of the research scene over the last years, and people are trying to find solutions. Molybdenum alloying has been shown to be one of these solutions, and a very effective one. Hydrogen-induced cracking is difficult to detect in steels, and particularly the underlying triggering mechanisms are extremely difficult to detect. The phenomena related to hydrogen-induced cracking are playing on atomic scale. on individual lattice planes at interfaces like grain boundaries or particle interfaces that are nanometer sized. So it is very difficult to do measurements or detect hydrogen at such features from an analytical point of view. So therefore, we actually need to define boundary criteria of how much hydrogen in general is allowable in a steel, what features should be avoided, and in what sense a microstructure should be optimized. But we can say for sure that alloying with molybdenum improves these features, and molybdenum by itself has a very beneficial effect against hydrogen-induced damage. The tendency of a steel to be subjected to hydrogen embrittlement can be lowered by optimizing the steel in terms of microstructure, but also in terms of what we call hydrogen traps to bind the hydrogen at certain features that are not so critical. And molybdenum alloying can play a significant role in achieving these microstructures and also in providing these traps.